Well, thank you very much. It is a pleasure to be here, and I'm glad I'm in the right place at this moment anyway. I'll try and talk a little bit about the challenge of climate change. I hope it's not too early in the morning to have a bit of science, but I thought I would give you a bit of the science of climate change and how that sets up the challenge in terms of the technologies and policies, and then hand over to Jonathan after that. So let's go back to the energy budget of planet Earth. So as I say, this is going back to square one, and I find this useful to do now and then, so I hope you do. Just to remind oneself that despite all the uncertainties around, there are some things we're pretty confident about. Well, we're confident about, here's our blue planet, and that's the sun's energy coming in. And that's what drives all our weather and climate and enables life on planet Earth. And given that solar radiation coming in, dependent on the distance from the sun, then the Earth heats up and gives off then long-wave radiation associated with being a hot body. And the temperature of the Earth, if you just had a situation like that, would be minus 18 Celsius. And life would not have occurred, and we certainly wouldn't be here today if that was the Earth we had. And that just went out into space there. Instead, we have this wonderful thing called an atmosphere around us. Sometimes it's a little bit grey like this today, but it really is a wonderful thing. And in particular, the greenhouse gases in the atmosphere. The atmosphere basically allows the solar radiation through. It has a little bit of problem with cloud now and then, as today, but basically the atmosphere itself lets the solar radiation through. And then the Earth heats up, as before. But then this atmosphere with its greenhouse gases that is transparent to solar radiation, the shortwave radiation, is actually opaque to the longwave radiation that absorbs it. And then it re-radiates it and back towards the Earth, which heats up the Earth as well as out into space. So eventually, then the Earth is going to heat up more until there is enough radiation leaving the planet to actually balance that coming in. But that's what keeps the greenhouse gases on our planet, makes it the temperature it is, and so are a good thing. And this then has been thought about for some time. Fourier, who was a mathematician, basically said there must be some process like this that keeps the temperature of the Earth as warm as it is. And Tyndall, who was actually a member of the forerunner of Imperial College, in 1859, 1860, measured this property of greenhouse gases as being absorbing heat and then re-radiating it. And the number one greenhouse gas is water vapor. And it's worth remembering that. You won't find too many displays around here saying, how can we reduce our water vapor emission to the atmosphere? Because however much we emit now, it's an integral part of the climate system, and if you increase the amount of water vapor in the atmosphere, now it would be back to where it was in a few days, having precipitated it out. So there's a cycle of evaporation and precipitation, rainfall, which controls the water vapor in the atmosphere. But the number two, carbon dioxide, is something we really do influence, and that's a lot of the discussion now. But there are many others we should remember, methane and CFCs, etc. So carbon dioxide, I've shown here a picture for the last million years, but let's remember that over the whole history of the Earth, as far as we can make out, there's been a story of the amount of carbon dioxide in the atmosphere and the temperature of planet Earth. Over most of the history of the Earth, there's been no ice at the poles, and the carbon dioxide levels have been very high. And during one of those periods where there was a lot of carbon dioxide, then the plant life, the biology of the climate system actually captured some of that carbon dioxide and put it underground, where it was turned into fossil fuel over the years. So when we use fossil fuel, we're really using biomass in a different form. So if we look at the last 650,000 years shown here, estimates of temperature along the bottom, and present day is on the right, and 650,000 years ago is on the left. And you can see the temperature varying through the cycle of interglacial, glacial periods. We're presently in an interglacial period with a minimum of ice in the polar regions, and the last one was about 120,000 years ago. And in between then, we had the cooler times with the ice sheets covering much of the northern hemisphere continents. But if we go to the carbon dioxide level in red, whenever the temperature of the Earth was high, there was a lot of carbon dioxide around, and similarly other greenhouse gases. And our understanding of this is that the whole system is controlled by the parameters of the Earth's orbit, and this determines how much radiation is being received in the northern hemisphere summer in particular. But then the greenhouse gases are an interactive part of the climate system and go to amplify those natural changes. So in the past, what we've seen is the greenhouse gases amplifying what would have occurred naturally. But then on the right-hand side, you see the difference where those curves are going up now, and that is almost inevitably due to our human activity, that spike there, taking the carbon dioxide levels way beyond where they've been over the last million years, back to a long time in the past. So this is the period over which we've actually measured carbon dioxide directly. I always have great respect for someone who in 1957, a young person who persuaded the funding authorities in the US that he should go to Hawaii and measure carbon dioxide. Isn't that impressive? So anyway, it's fantastic that he did. And so we have this record of carbon dioxide. It stays in the atmosphere long enough that it's a well-mixed gas, so it doesn't matter too much where you measure it. And you can see, well, the red curves shows the annual cycle of carbon dioxide, and we understand that because the northern hemisphere has much more of the vegetation than the southern hemisphere. In the northern hemisphere, it soaks up some of the CO2. In the autumn, it gives back some of the CO2. And so we see the sort of biosphere of the Earth breathing, if you like, in that red cycle there. But then you see the upward motion there of the curve, up to about 395 or so parts, depending which time of year, 395 parts per million. Now, during the Ice Age, it oscillated between about 180 and 280. So we've already taken it up at least 40%. Above what was the cycle before. And given the intimate relationship between the greenhouse gases and carbon dioxide and the Earth's temperature and its whole climate, it's clear we may be doing something quite serious to this system. I wanted just to emphasize this then in terms of carbon dioxide. It's risen by this large amount, and we can be extremely confident from a number of lines, which I won't go into, that it's due to our activities. Land use change dominated to start with, but then for the last 100 years, it's been principally the burning of fossil fuels that have done this. But just to give you an idea now, if we add 100 tons of carbon dioxide to the atmosphere now, come back in 20 years, you'll find 40 of them, not the same molecules, but the influences there. And if you come back in 1,000 years, there'll still be a quarter of it left, and 10,000 years, there'll still be 20 tons of it left. So it's one of those things you can't just say, oh, well, we'll keep going now doing what we like, and if it doesn't look too good, then we'll stop. I'm afraid carbon dioxide isn't like that. Once you've emitted it to the atmosphere, you either find some means of getting it back, capturing it, or else if you leave it to the natural systems, then it's going to take a very long time. It isn't just carbon dioxide, and this is a picture from the previous IPCC, the Intergovernmental Panel on Climate Change. The next one will have a similar picture that won't be very different. And what it shows is, in the terms of the sort of discussion I gave you at the beginning, what is the imbalance of the energy budget of our planet due to the greenhouse gases that we've had at the moment. And CO2 is there as a long-lived greenhouse gas. But then there's methane, nitrous oxide, halocarbons. The timescale of methane staying in the atmosphere is more like a decade. So certainly the methane there, if we put some there and we stop, then in 30 years' time we could say there may be a little bit of residual warmth in the climate system, but the effect apart from that will have gone. Ozone, tropospheric ozone is a nasty pollutant, and it also plays a role in air quality in various aspects, as well as in the climate system. But going to some of the other things then, the blues there, the bars there show the uncertainty, and the uncertainty has perhaps decreased somewhat in this past period, But there's no doubt some of the particles we put into the atmosphere actually tend to stop the solar radiation reaching the Earth and tend to cool. I think the next IPCC is liable to have an estimate of the cooling which is slightly below the estimate here. But the total effect then is about the same as the CO2, but there's lots of pluses and minuses. And there's an estimate of the impact of solar changes there, and again, our latest estimates won't be very different from that. So it's not to say the sun changes in the total solar irradiance aren't important. They are, but at a much lower level than the greenhouse gases. Now, if we say, well, given that addition of greenhouse gases and into the future, the Earth will warm, there's no doubt, and almost no dispute on that. And the only question is how much. And let's look at the past then, and we see a typical rough record there from the past that goes back to 1850 or so. And there's curves from 3 different climate centers there who've done this sort of analysis. And there was a group of physicists in California who thought that really these climate scientists weren't very good at science and that they'd do it properly, and they were funded by the Koch brothers to do this properly, and they actually, to their credit, published their answer and said, we get almost exactly the same as these other curves. So however you do it, you get something like this. And you can see there's fluctuations. Without us around, the climate system would have fluctuated, and it has done. But you can also see that over the period, there's been a rise of about 3/4 of a degree over that period. If you smooth the curves, a 10-year running average, 20 years, 30 years, you see something which still has multi-decadal variability in it, but you do see also a much clearer version of the trend, which is entirely consistent with the greenhouse gases we've added. But there is multi-decadal variability, and that multi-decadal variability, there's no doubt, was acting in the same sense as the greenhouse gases in the 1990s, leading to a very rapid warming. And it's almost definitely in the opposite sense at the moment, where it's counteracting the trend. The hiatus in warming that we've had over the last decade or so is not present when you look at the average of the models, but when you look at, because what we're doing is comparing one planet Earth with the average of 1,000 models, where you get rid of all those fluctuations. But if you look at the individual models, they all contain decades or more where the whole climate system cools. So this is entirely consistent with what happens in those. At such times, the heat was given from the surface towards the deeper ocean, and there's evidence of that occurring at the moment in our climate system. So it'd be extremely surprising if warming doesn't start going over the next decade or so. The other evidence of warming, well, there's lots of them, but I'm just going to show a few. Again, since we've been able to measure sea level from satellites, it was done before from tide stations around the world, but the measurement from satellite is probably more accurate. And over this period of since 1990s, then we're looking at something like 3 millimeters per year of sea level rise. And that doesn't sound much, but it's 30 centimeters per 100 years. And that's in this past period. And most of that was due to the expansion of the ocean. Water doesn't expand much when you warm it up, but if you have 4 kilometers of ocean and you warm it up, then it does expand in a measurable amount. But it's estimated in this last period about 1 millimeter per year is actually due to the melting of Greenland and the Antarctic ice sheets. So there is an increasing contributor from the ice sheets. And the best estimate that is likely to come out from the next IPCC by the end of the century is probably about 1 meter of sea level rise. So, and then Arctic sea ice has been an interesting thing. So the Arctic sea ice grows through the winter season, reaches a maximum around now, and then starts to decay again through the summer season, where it reaches a minimum in mid-September. And the area of that Arctic sea ice, the curve on the right, when it reaches its minimum, has again the sort of fluctuations of a geophysical series. And if you looked at that up to this, you can't see those days, but up to about 1995 or something, you could say, well, it looks about level. But since then, it's become very obvious that there is a trend on the whole series. And I think if we say there's a trend, that's the best outlook we can have, because that trend would mean that by the 2050, 2060, we could expect the Arctic sea ice to perhaps disappear, but then reappear again in the next winter. But if you look at 2007, that was the minimum there, before last. Then there was a lot of interest in that, and if you read your Greenpeace news, the Arctic sea ice was going to disappear in a few years. And then, of course, it came back again over the next couple of years, and then if you read your Global Warming Policy Foundation, it had all gone away, and there was no problem. I think the reality is somewhere between those two, and 2012 was the minimum there. And what we see is actually the sea ice is becoming, the old sea ice is tending to disappear. So most of the sea ice that develops over the winter is just 1 year old. It's thinner, and it is now more vulnerable than it was in the past. So there's a big question now about whether we are really seeing an accelerated rate of that sea ice disappearing, or whether it is going to go back to that trend. So there's no doubt the climate system is warming. Now, if we go to the future, we can use back-of-the-envelope calculations, or we can use put all our understanding of the climate system, Newton's laws of motion, the equations of thermodynamics, into computer models that exercise the biggest supercomputers around. And so this is done, but always, as I say, it's not just very complex models and we have great confidence in what comes out of them. It's always an idea of using a whole range of understanding and a range of models. But if you take these top-of-the-range models and you try and say, well, how good were they if you look at the 20th century? Well, it's always a question, well, if you want to see things looking bad, you can see them. But if you want to say, well, that's pretty impressive, you can also see that. So if you take the average of all these models and look at the annual precipitation, then the observed one is on the top and the modeled one is on the bottom. And I won't go into detail, but it's pretty good when you say this is done from square one, starting with Newton's laws of motion, and you can get a rainfall pattern looking like that. And the phenomena that occur are pretty impressive as well. If you look at a single point on the Earth, you can say it's not quite right, but so be it. Now, if you run these models and look at the trace of the temperature over the 20th century, then the observed trace is in black there, and the range of the models is in yellow, and the average of the models is in red. And you can say, well, the average of the models isn't a very good representation of, except in terms of the trend, but nearly everywhere, well, everywhere, I think the observed is within the range of the models. However, if you don't include the greenhouse gases and the changes in those, the changes in the greenhouse gases, then you get the blue curves here. And it is inevitable, really, that the increase in temperature that's been observed cannot be simulated by these models without the increased greenhouse gases. Now, it's a sign the models are working well, but equally, I have to say, there's a certain sociology of modeling and the way one decides how much aerosol should be in the models, that if the answers of a model weren't roughly doing this, perhaps they would have been looked at to see what was wrong. But it is pretty impressive the models are working quite well. Now, if we look at the signature of something like the sun, if you just put changes in the sun in a model, you find the atmosphere warms everywhere. If you put changes in greenhouse gases, I should say this is North Pole on the left, South Pole on the right, and vertical is the vertical domain. So you find, if you put greenhouse gases in, that the stratosphere, the higher atmosphere, cools and the lower atmosphere warms, and that's what we've actually observed. So you can do all sorts of things in the model and say, do we see the fingerprint of the sort of greenhouse gases in the changes there? So looking forward then, this again was the last IPCC, the next one's not going to be very different. It's going forward from the year 2000, and it depends on the scenario you have for human activity and the emissions associated with that, which one you get. So the bottom one is if we didn't emit any more greenhouse gases, so that's not possible. But the lower ones suggest a warming by the end of the century, maybe slightly below 2 degrees, but with a range, whereas the upper ones suggest more like 4 degrees Certainly if you go from pre-industrial, that's 4 or 4.5 degrees. So it depends which one you take, what we do. But you don't see the difference until beyond 2030, 2040. So we're already committed, really, to the warming over this next period. But if you take that sort of green scenario there, which is the sort of line we're going down at the moment, the green or the red one, then if you look in the geography about the change, you see that everywhere around the Earth, on the continents, the change is more than that global average. So we talk about global warming and 2 degrees or 4 degrees. You should always remember that means more on the continents. Over Africa, it means more than 3 degrees in this one here. And if you go to the northern continents in winter, it means something like 2 or 3 times that global average number. So something of the order of 8 degrees or something over the northern continents in winter. So you can imagine the impact on the permafrost and on the Arctic sea ice. But also I want to say, if you look at this picture, you will see that the temperature contrasts change. So between the North Atlantic and us, you can see there's a large difference in the warming. Now the weather systems feed off those temperature contrasts, so the weather systems would be very different. The whole climate would be different. And if you go to changes in precipitation, less confidence in general, but the warmer polar regions getting more precipitation, the subtropical regions like the Mediterranean having even more problem not getting their winter precipitation, and other areas of the world as well. So the rainfall would change as well. When you look at a global mean, this is actually saying, well, if we look at a decade at the end of the 21st century, globally, what can we say for that? What do the models suggest for the probability distribution for the temperature change for that last decade? And you can see that overwhelmingly they say positive. It's even possible to get a decade at the end of the century where there could be cooling. That's what this says, although most of them give a pretty strong spike for a warming. But when you come to Europe, you see a broader distribution. So Europe could easily have a decade which cooled, although the average would be warming. And when you come to the UK, then the shift of the distribution is actually hardly visible compared with the wings of the distribution, the breadth. So the average is a warming, but that certainly wouldn't happen every decade. And just to emphasize one thing that I think the climate models, we shouldn't have utmost confidence in them, say they are bound to be right. But I'm going to suggest that one of the things is that I suspect they could be wrong is in their robustness, which is almost too conservative. They want to stay near today's climate. And don't worry about all these pictures. They're just different scenarios for different decades. And what you see is the same temperature pattern for change, but just with a different amplitude. And our understanding of complex systems, complex dynamical systems, is that we would expect with these large changes on the bottom right, that there would be a fundamental change in the system. Yet the models don't do this. Are there thresholds around in the climate system? And our understanding is that there probably are, but we don't quite know where those are, where the system will change in a big way. If there aren't thresholds in the natural system, in the social system, as you pre-monsoon India or Bangladesh is 5 degrees warmer. Can you imagine that? I mean, it's already 40 to 45. You add 5 degrees onto that. Can we really live, can the social systems really keep going? As the sea level has risen in Bangladesh, we don't like migration now, but you think what's going to happen? Where are all those Bangladeshis going to go? I don't know. So some of the things in the last decade, we haven't had a global warming that much, but the number of extremes has been quite impressive. The 2003 heat wave in Europe, this is from Switzerland, showing the distribution and the individual years before 2003. 2003 came along, my goodness, you can't say that's a 1 in 100-year event because there's no Gaussian that fits into. It's just off the scale completely. And the same was true in 2010, where these are sort of 4 or 5 standard deviation events, or actually the maximum was 5.5 there. On a monthly time scale, it was a a 5.5 standard deviation event in Western Russia. I think Russia felt pretty cool about global warming, if I can say that, until the fires around Moscow and the warmth and the drought that goes with that. The US this summer, incredible warmth and drought and the impact on food there. And there's work by Jim Hansen that suggests that if you look around the world and compare with the local variability, that the number of the frequency of excess heat in the summer has really increased over the period, the shift to the right of those changes in the number of heat waves. I'm not going to say everything's got warmer. I think we've seen some very interesting cold spells as well. So there was a record winter in 2009-10 for Eurasia, and a record cold in December 2010 for the UK. You note that the whole northern hemisphere was pretty warm actually during those spells. It's actually a very interesting weather pattern that occurred there. There was one day when I remember the temperature wasn't going above freezing in London, and I looked at Greenland and it was plus 10 in Greenland. And you can see, you think everywhere's cold. Well, actually, it's just there was an extreme weather pattern. And one of the things we've got to really watch again is, are we going to get increased variability? And that's something that's not clear. But to go towards the other stage of this challenge then, I've already emphasized some of the changes, but it's the context of a world population which is growing and maybe will stabilize and start to decrease at about 9 or 10 billion. And the need for development, the poverty challenge, the hunger challenge. And then we've got people becoming more middle class around the world and a changing diet, wanting to change to more meat rather than basic cereals, etc. And increased demand for food, water, and energy, and also the other global environmental changes. So climate change is in the context of those. And the impacts, really, I'm not going to go through them. I'm sure you know them here. Huge. And, of course, ocean acidification goes along with carbon dioxide as well. So, I think the things that climate models are showing us are what's going to occur if we're lucky. If we don't get some of these major threshold changes, that's what they're showing us. And I believe there will be an increasing chance of crossing those sorts of thresholds. So, I sort of sum it up. We don't know the details of what it's going to mean, but we do know that by emitting these greenhouse gases, we're performing an extremely dangerous experiment with our one planet. If we had 1,000 planets, you might say, well, let's try this on a few of them and see whether, if we don't like it, then we'll go somewhere else. Well, we don't have that option. We have one planet, and we are now at the critical period for that planet about really whether our species is going to be able to continue the way it wishes to develop over this next period. And if this is Russian roulette, I think there's one empty chamber and there's about 50 chambers with bullets in. Now, are you willing to take that risk for your children and grandchildren? I'm not. So let's see what we can do. So we can adapt, okay? And this is part of what I had to cope with last night with Peter Lilly and co. Was actually, let's get as rich as we can over the next 50 years, and then we'll look and we'll be able to do, we'll build a wall around ourselves and we'll be so rich we can do it. I don't think it's going to be like that. But we certainly have to adapt to changes, and developing a robust resilience in everything we do is going to be very important. Do something else to compensate. Well, the good side of that is removing carbon dioxide from the atmosphere. It's probably easier to stop the carbon dioxide getting there in the first place, but if we could get techniques to get it back again, great. Or reduce the sun's energy reaching us. And then finally, mitigation. So I was going to show you the ranges. I think I'll skip that bit. So that adapting, we're not sure. If you're thinking in Lincolnshire, what are we going to adapt to? It's still a very broad distribution of outcomes. So we really should be developing the robustness, the resilience. If we are robust and resilient to the last 30 years, plus a few degrees, and plus a few more excess rainfalls, and also a few more droughts, then we can probably manage. So, but then geoengineering, I've already said, if we have techniques for removing carbon dioxide, great. let's do that, although I think it would be easier before. I just want to say a little bit about solar radiation management, which is the sort of the Texan solution, if you like. I mean, this is, okay, we've stopped the energy leaving the Earth, so let's stop some of the sun's energy coming in. And the favorite one of those, we can put umbrellas in space, a little bit expensive, but anyway, or we can put more particles into the stratosphere, the middle one here, mimicking what volcanoes do, or we can try and help the low clouds. I'm not sure I like that today, but anyway, try and get droplets from the ocean, put them into the atmosphere and encourage low clouds, or we can make sure the surface is a bit whiter than it was. I think the only one of these that's really is likely to be really tried is the putting the particles into the stratosphere. It could be done, and you do it in the equatorial region with rockets or special jet aircraft, and then those particles would spread over taken by the circulation towards the polar regions and then come down again. They give you some very nice sunsets. Now, we do know that putting things into the stratosphere has given us a problem already with the ozone in the stratosphere, which actually protects us from ultraviolet radiation. And I think the perturbation to the stratosphere would be something to really worry about. The other thing to say is that, well, two more things. One is if we did manage to balance the global energy budget, still the climate would change, because you wouldn't balance it in space and time, only on the average. So there still would be a change in climate. And the third thing is to say, once we've started, we have to continue, because once we stop, then we'll realize that energy imbalance and get an incredibly rapid warming. So there's a sort of legacy of hundreds of years of having to do this. So I'm rather biasing you, but I think mitigation sounds like a better option to me. We do have to do adaptation. So internationally, we have a framework from the UN, not seen as fantastically successful. Copenhagen, I'm sure you shared in the joys and the pain of Copenhagen, and since then, and some measure of actually saying the last few that we have to get an agreement by 2015, and everyone, all involved in that, saying we need that, in place by 2015 to be active by 2020. And the EU's been having its objectives. Will it move to a 30% reduction? Well, we hope so. And it has objectives later on and renewables target. I think one of the things that's been emphasized in recent time is the number of countries around the world that actually, or regions of countries that have their own targets. So they haven't been forced to have them, but they have them. And I'll just take one example, China, sort of saying their carbon intensity will actually, they've got a target sort of 45% reduction in their carbon intensity over the next couple of decades. And that's pretty impressive stuff. And China is actually aiming to make itself a leader in the technologies as well. And I do know, I'm a member of the Chinese Academy of Sciences, so I know some of their thinking as well, and they are extremely worried about their climate changing, given their population and their agricultural dependency. So the UK, I have gone around the world saying this is one thing we can be incredibly proud of having our climate change bill. There's only Peter Lilly and 4 others that voted against it in Parliament and 450 for it, so it went through with great support. And this pledged us, as you probably know then, to reducing our CO2 emissions by at least 80% by 2050. And importantly, it has this 5-year budget system that we've set up. And so the Climate Change Committee that I'm on, which is definitely independent and offers advice and monitors what the government is doing. So we've advised on these targets, which now take us through to 2027. And so it's not just a government can say, well, come back, we'll let the next government deal with the 2050 target. There's actually a legal reason they have to be going towards these interim targets. So I wanted to just sort of finish by telling you about, just reminding you again about how we specified or advised about this 80% target. And I hope it's consistent with the sort of ideas I've been giving you. We don't know, everything's a probability. So we said, pose 2 criteria for the global emissions and the consequences of them. there should be a 50-50 chance of not getting much above 2 degrees. 2 degrees is not magic, that 1.9 is fine and 2.1 is disastrous. It's an indication of a range. So I would be a happy man if I thought we could actually make global temperatures peak at around 2.4 this century, rise. But we said there should be a negligible chance of getting to 4 degrees, because 4 degrees means huge changes, if we're lucky, just in the climate we have. But there may be there's quite likely to be those thresholds. So that's what we specified, and we looked at global emissions that went with that and came to these sorts of curves here. The blue one is the sort of thing we're doing at the moment. The green is where global emissions should really be going, peaking somewhere around 2020 or so, and dropping by about 3 or 4% to a low level after that. Now that's pretty punitive stuff, but actually even that, if you look at the right there, it gives a median probability of getting just above 2 degrees, but there's still a 10% chance of getting to 3.5 degrees by the end of the century with current knowledge. So that's where we are. So if you look at this curve here on the left, then by 2050, the global emissions have to be at least 50% lower than they were in 1990. So that's a 50% reduction. Seeing the UK was 5 times the global average in 1990, that's where our factor of 10 comes down, because if we say we apportion this equally around the world, I said that slightly wrongly. So if we apportion this equally around the world, it's slightly over 2 tons of CO2 per person in 2050. And the UK was at 10 tons of CO2 per person, and that's where our 80% reduction came from. So that's what's enshrined in UK law. And my very last slide then is say, this is the challenge to us. There's our 2050 amount that we're allowed. Here's our 2006 emissions and the various sectors through which, and their contributions. Every sector has to contribute if we're going to reach that. And certainly a basic way that we've said this has to be approached is by decarbonizing the electricity supply. And having done that and almost removed this yellow bar at the bottom, you then get into the domestic transport using electricity and much more in the residential and industrial processes as well. So we start to really eat up there. But I hope I've described to you the scientific challenge and actually the challenge to us. And this is what I hope you're going to help us do. Thank you.